Hello everyone and welcome to the 13th episode of CPP Next. In this episode we will explore switch cases and lookup tables. Which one should we use and what is the performance difference? Please like and subscribe, and without further ado, let's start exploring. Then we will be using QuickBench to understand the difference in performance. QuickBench is a great site and it's really easy to see the difference in performance and measure quick benchmarks, really small ones, without installing Google Bench. So what will we do here? We will create a small program that will use mathematical functions just for simplicity. Let's say we have plus, minus, molten div. I want to create one random number just to make sure that the compiler will not optimize out things during compilation. So we are creating this random number here. Afterwards, we are creating a simple case math function. That means that we are using an O, that is an integer that initialized to 0. We are doing the loop for the performance. And in the loop, we have a switch case. Each switch case is for an operation from the oper enum. And we're just doing the operation inline. That means those operations will be inline, no function calls and nothing here. We are using benchmark do not optimize out just because we need the compiler not to optimize out these operations, basically to make sure they're not optimized out. Afterwards, we're using a lookup table. So we're creating a very naive lookup table with stud map that is mapped to oper and stud function. Each one of those nodes in the map is an oper and a lambda function. Pretty easy. This is one of the best things about lookup tables. It's really easy to implement and it looks much cleaner and better than a switch case. So in this function, you can see we have just one line of code. It's very function program-like, and we are just using the add function to get into the map itself, and then providing O with the Z and O, just two numbers that we need. So what about performance? As you can see, maybe the code is cleaner, but our performance is 2.5 times slower than the simple switch case. There are many reasons for that. So let's start exploring one by one how should we implement the lookup table correctly so it will not be so harmful for us to use it. The first simple fix is to remember that stud function is basically something that uses type erasure. To use type erasure, it needs to copy the data types from place to place. And that means the performance hit might be harder. What shall we do here? We can use stud add pointer t, that is basically creating a function pointer. Each one of those lambdas can be used as a function pointer with a plus. And in this case, we don't even need to do the plus. I just want to be very explicit here. So we have created a new map that uses function pointers with the lambdas. And as you can see, the function itself is almost the same. We are just using ln2 here. And we are accessing the new map. Let's see what happened here if we will use flag 10. As you can see, we got what we expected to get. The performance got a little bit better. Instead of being 2.5 times slower, it's just 2 times slower. So that's great, but let's look what will happen with flag 17. Surprise, surprise, the performance got a little bit worse, but I would say it's just noise. Basically, it's the same as lookup naive now with the newer compiler. What does it mean? It means that the newer compiler can look into a std function a little bit better than the older compilers. And again, this is straightforward, explains why using newer compilers is better. Your performance will get better with newer things, and each compiler does it work a little bit better, so we will benefit from it. Don't get stuck with your old compiler forever. But because the newer compiler does the job a little bit better, we need to explore further. What else can we do here? Let's try to understand why we have the performance hit. Let's remember, stud map is a red and black tree. To access a member in a red and black tree, you have to use a log n operation. That is pretty slow. Let's not forget that beside it, the memory is scattered. So maybe the better way to use it will be with an unordered map. An ordered map is a hash table. Hash tables depend on implementation. Let's see what will happen if we will use an unordered map. As you can see, All we changed is basically to use an unordered map, and we're using the same functionality. The function itself looks very, very similar. We're just using lm3. And as you can see, nothing changed. So good hash implementation is not good enough for us. We're still seeing bad results. Let's try to explore it further. We will give unordered map another chance. But this time, again, we will try to use function pointers instead of stud function with type erasure. What will happen here? As you can see, lookup hash no function got better than it was with stud functions. That means if you can use a function pointer, the compiler still will be able to do a better job than with the stud function. It's not always possible to optimize stud function correctly. In this case, we got what we wanted. Hash no function is 1.3 times faster than lookup hash. This is not bad at all, but we're still slower than cache math. What can we do here? Now, I mentioned that we are using something that might scatter the memory. That means that the access to the cache will be worse. That means we need something that uses locality. And we have this data type. It's called a vector. Let's try to implement a lookup table with a vector. As you can see, in this case, the change is not dramatic. We are using a stud vector of functions. And instead of giving it a key and a value, we are just giving it a value. Then the usage is almost the same, just a little bit simplified. So let's find out if it will be better. And yes, we got faster, much faster than before. And this is because now we have the locality. Everything is in the cache now. So that means we're not using access to the memory again and again, because accessing the memory is much slower than accessing the cache. This is what's so great about locality. But we still have a problem. We're slower than case math. And we still need to do something here. Let's not forget that here we used stud function again. What will happen if we will remove the stud function and we'll use function pointers? Let's try. And again, the change here is pretty simple. We are just using the add pointer t type trait. That means we will use function pointers here, and all the lambdas will become function pointers. Then the usage is almost the same as before. Now, let's try to see what will happen. As you can see, we got faster than case math in this case. That means we finally got what we wanted. Still, you have to understand that this might be some noise. Lookup vector function might get a little bit slower or a little bit faster than case math, depends on the state of the cache. But that's not so bad. We got to the lowest level of the code, to the best optimization, with something that looks much better than a switch case. What is the moral of the story? The moral is that you have to understand what you're using and how are you using it. We need to get to understand our data types, and we need to understand how to use those things correctly. We need to understand that we have a cache and a memory, and our CPU might be different. So try to understand the hardware that you are using to get better performance from your software. Thank you for watching, and see you in the next episodes.